Press 2 fingers against the right side of your abdomen, just below the curve of your ribs. There. That is your liver. Right now, depending on what you have eaten today, it is doing one of 2 things. It is either filing away glucose into long branch chains for later, or it is pulling those chains apart, releasing sugar back into your blood, one molecule at a time, to keep your brain alive. I want to tell you about what happens inside that organ, and inside the rest of you when you skip breakfast 3 days in a row. Not fast for 3 days. Just skip the morning meal. 3 times. Keep eating normally otherwise. The story is more interesting than I expected when I started looking into it. Let me give you the layout first. You have, between your belly button and your collarbone, a small machine shop. The liver weighs about 1.5 kilograms. It sits under your right rib cage, slightly larger than your 2 fists pressed together. And it carries, at any given moment, between 80 and 100 grams of stored glucose, 300 to 400 calories. The whole bank account. Out beyond the liver, in the meat of your arms and legs, there is another reservoir, your skeletal muscle. About 400 grams of glycogen lives there. But here is a thing I find pretty wonderful. Your muscles cannot share. They lack an enzyme called glucose 6-phosphatase. So muscle glycogen is locked in. It can fuel the muscle that holds it. It cannot leave to feed your brain. The liver is the only organ that can release glucose back into the bloodstream for general use. Your brain, about 1.4 kilograms of meat, sitting between your ears, demanding 20% of your body's resting energy. It uses 120 grams of glucose every 24 hours. Without resupply, the liver's pantry runs dry in roughly 12 hours. And then, sitting under your skin and around your organs, there is the warehouse. Adipose tissue. Fat. The average adult carries somewhere between 50 and 150,000 calories of energy in those cells. Compared to the 400 calories in the liver, it is an ocean to a teaspoon. Now the question that interests me, if you carry an ocean of fuel and only a teaspoon of immediately accessible glucose, why is most of your day spent burning the teaspoon? Why is the ocean almost untouched? The answer is in a single hormonal ratio, insulin to glucagon. When you eat, insulin rises. When insulin is high, the warehouse is locked. The fat cells will not release fuel. The body burns the teaspoon, refills the teaspoon, burns the teaspoon again. The ocean stays still. To open the warehouse, even a crack, you have to let insulin fall. And the only way to do that is to stop putting glucose in your mouth. That is what skipping breakfast does. Mechanically, it is not a diet. It is a hormonal lever, pulled 3 times. So, day 1, you eat dinner at 6 in the evening. By 6 the next morning, 12 hours have passed. Your liver glycogen has been quietly draining the whole night, feeding your brain through the dark. By the time your eyes open, you have used roughly half of it. Now here is what you do. You skip breakfast. You drink your coffee. You go to your desk. The clock moves to 9, then 10, then 11. Inside your liver, a hormone called glucagon, not glucose, glucagon, made by the alpha cells of your pancreas, is rising in your bloodstream. Glucagon tells the liver one thing: cut the chains. Release the sugar. The enzyme that does the cutting is called glycogen phosphorylase. Pretty descriptive name. It clips 1 glucose unit at a time off the branched glycogen molecule. By 11 in the morning, your liver is feeding your blood at the rate of roughly 7 grams of glucose per hour. Almost all of it going to your brain. George Cahill, a physician at Harvard, spent 40 years studying what happens when food is withheld. He published the foundational papers on starvation metabolism in the New England Journal of Medicine and the Journal of Clinical Investigation through the 1960s and 70s. Cahill showed that liver glycogen depletes within roughly 24 hours of fasting in a sedentary adult. By skipping breakfast, by extending your overnight fast from 12 hours to 17 or 18, you push your liver to the edge of that pantry, not over, just to the edge. And in that edge state, your body does something that I want you to understand precisely. It begins building glucose out of nothing. Well, not nothing. Out of something. Out of amino acids it pulls from your skeletal muscle. Out of glycerol it pulls from your fat. Out of lactate that comes back from working tissue. The process is called gluconeogenesis. New glucose. Made on demand. Built from spare parts. This is also why, around hour 15 or 16 of an extended morning fast, your cortisol stays elevated above what it would normally be. Cortisol is one of the hormones that signals gluconeogenesis to ramp up. The mild stress response is functional. It is asking the body to assemble its own sugar. And here is something else. Around hour 14, your stomach produces a hormone called ghrelin. Ghrelin is the molecule responsible for the sensation you call hunger. David Cummings, working at the University of Washington in the early 2000s, showed that ghrelin pulses on a schedule learned from your eating pattern. If you have eaten breakfast at 7 in the morning every day of your adult life, ghrelin will rise sharply at 6:50. Your stomach is anticipating. The hunger you feel at 7 on day 1 is not a deficiency signal. It is a habit signal. By day 2, the 7 o'clock pulse is smaller. By day 3, smaller still. The hunger is rescheduling itself. So while glucagon was rising and ghrelin was teaching itself a new clock, something else had already begun in your fat tissue. Lipolysis. The releasing of fat. In your adipose tissue, an enzyme called hormone-sensitive lipase had been waking up for hours. It does what its name says. It clips the fatty acids off the triglycerides stored inside your fat cells. 3 fatty acids. 1 glycerol backbone. The fatty acids drift out into your blood, latched onto a transport protein called albumin. The glycerol, that goes to the liver to be turned into glucose, contributing to the gluconeogenesis I just described. But the fatty acids go to the liver too. And in your liver, in the mitochondria of every hepatocyte, a process begins that you do not run during normal eating. It is called beta oxidation. The liver chops the long fatty acid chains into 2 carbon fragments called acetyl coenzyme A. And when the demand for glucose is high, when oxaloacetate is being pulled away to assemble new sugar, those acetyl coenzyme A molecules pile up. The liver does the only thing it can do with the surplus. It welds them together into ketone bodies. 3 of them: acetoacetate, beta-hydroxybutyrate, acetone. By hour 18 of an overnight fast, by lunch on the day you skipped breakfast, beta-hydroxybutyrate in your blood has risen from a baseline of about 0.1 millimoles per liter to somewhere around 0.3 to 0.5. By day 3 of repeated breakfast skipping, with each morning fast extending past hour 17, that number can climb toward 1. Mild ketosis. Not the 4 to 6 millimole readings of a multi-day water fast, but measurable, detectable, real. Now I want to introduce you to a person whose name belongs in this story. Richard Veitch. He worked at the National Institutes of Health for decades, studying ketone metabolism with a level of precision that bordered on obsession. Veitch demonstrated, with isotope tracing studies in the 1990s, that ketone bodies are not the metabolic garbage of starvation that the textbooks once called them. They are a clean, efficient fuel. When a mitochondrion burns beta-hydroxybutyrate instead of glucose, it produces about 30% more ATP per unit of oxygen consumed. And it produces fewer reactive oxygen species. The cellular wear and tear is lower. Veitch argued for years that ketones should be reclassified, not as an emergency fuel, but as a preferred fuel, under conditions of substrate scarcity. He was right. The literature has caught up to him slowly. What this means in your body on the 3rd morning of skipping breakfast is something you can almost feel. The brittle blood sugar swings of the early hours have settled. Your liver is producing a steady mix of glucose and ketones. Your bloodstream carries both. Your tissues are pulling from both. The metabolic noise has quieted down, and the person who has been eating cereal at 7 in the morning for 40 years because their mother told them to, the person who feels guilty skipping a meal, The person who has been told, repeatedly, that breakfast is the most important meal of the day. The person whose blood sugar crashes at 10:30 and reaches for a pastry to fix it. That person is, on day 3, somewhere around 11:30 in the morning, experiencing a kind of stillness in their body that they have not felt in a decade. The hunger has loosened its grip. The crash never arrived. Something has changed. And as those ketone bodies started leaving the liver, drifting in the bloodstream, they did something glucose cannot do. They crossed the blood-brain barrier. Now look, the blood-brain barrier is a wall of tightly joined endothelial cells that surrounds the capillaries of your brain. It is not an open door. Most molecules cannot pass. Glucose has its own dedicated transporter, a protein called GLUT1, that ferries it across. Without that transporter, your brain would starve in the middle of a meal. But ketones, beta-hydroxybutyrate especially, have their own transporter. It is called monocarboxylate transporter 1, MCT1. It sits in the same membrane and pulls ketones across into the brain tissue. By the 3rd day of skipping breakfast, your neurons are receiving a small but steady drip of ketones during the late morning hours. Stephen Cunnin, a researcher at the University of Sherbrooke in Quebec, spent decades imaging the brain's fuel uptake using positron emission tomography. He showed that as blood ketones rise, the brain's preference shifts. At a blood beta-hydroxybutyrate concentration of 1 millimole per liter, the brain pulls roughly 10% of its energy from ketones. At 3 to 4 millimoles, which you do not reach by skipping breakfast, but which appears in longer fasts, the figure climbs towards 60%. You do not get there in 3 mornings. I want you to be clear on that. What you get is the beginning, the first whispers of fuel flexibility. A brain that has run almost exclusively on glucose for 30 or 40 or 60 years, suddenly remembering, around 11 in the morning on day 3, that it has another menu. And here is something else Cunnin found. And Mark Mattson at the National Institute on Aging confirmed in animal work and in human studies. The neurons that take up ketones use them more efficiently per molecule of oxygen than they use glucose. They produce less reactive oxygen species. The cellular signaling pathways that promote stress resistance, pathways involving a protein called brain-derived neurotrophic factor, BDNF, are upregulated. Mattson's work, much of it published in the New England Journal of Medicine and Cell Metabolism between 2007 and 2021, showed that intermittent fasting in laboratory animals raised BDNF levels in the hippocampus. The hippocampus is the seahorse-shaped structure on each side of your brain that consolidates memory. Higher BDNF in that region is correlated in animal models with improved learning and resistance to neurodegeneration. Now, and this is important, most of that work is in mice. The translation to humans is suggestive, but not settled. I will come back to that. What I want you to hold for now is the picture. Day 3, 11 in the morning. Your brain is being fed by 2 streams. Glucose flowing through GLUT1, ketones flowing through MCT1. Your neurons are firing on a fuel mix that, in evolutionary terms, you were almost certainly designed to use, since for the great majority of human history food was not waiting for you the moment you opened your eyes. Your ancestors hunted before they ate. They walked before breakfast. The morning fasted state was the default. The fed state was the reward. And while your neurons recalibrated, deep inside every cell in your body, a more interesting process had been waiting for its moment. Autophagy. Inside your cells, you have a system that performs a kind of housekeeping. Picture an old workshop. Over years, broken tools accumulate. Dust gathers. Damaged machinery sits in corners. The workshop has a janitor, small membrane-bound vesicles called lysosomes, that can engulf the broken parts and break them down with acid into raw materials, which the cell then reuses. This process is called autophagy, from the Greek auto, self, phagy, eating. The cell eats itself. Autophagy is happening in you right now, at a baseline rate, but it is suppressed when your cells sense that food is plentiful. The molecular sensor that does the suppressing is called the mechanistic target of rapamycin, mTOR for short. Almost every cell in your body has it. When you eat a meal, two signals come in. Insulin from your pancreas telling your cells that glucose has arrived, and amino acids, leucine in particular, telling your cells that protein has arrived. mTOR senses both. It activates, it tells the cell to grow, to build new proteins, to divide, and it tells the lysosomes to slow down. The janitor goes home. Now I want to walk you through what happens when you skip breakfast. Insulin falls. Amino acids in your blood decline as your tissues use them for fuel. mTOR senses this and quiets down. And as mTOR quiets, another sensor, adenosine monophosphate activated protein kinase, AMPK, wakes up. Because the ratio of AMP to ATP inside your cell has shifted, the cell knows it is in a low energy state. AMPK rises. mTOR falls. The lysosomes, the janitors, go back to work. They begin to engulf damaged mitochondria, misfolded proteins, the cellular detritus that has accumulated since your last extended fast. Yoshinori Osumi at the Tokyo Institute of Technology is the scientist who unraveled the molecular machinery of autophagy. Through the 1990s, working with brewer's yeast, he identified the genes that control the process. 30-some genes. The ATG family. He won the Nobel Prize in Physiology or Medicine in 2016 for that work. What Osumi showed, and what later work in human cells confirmed, is that the autophagy machinery is conserved from yeast to humans almost without modification. The same molecules, the same signals, the same response to nutrient scarcity. There is a particular form of autophagy that I want you to know about. Mitophagy, the selective recycling of damaged mitochondria. Your mitochondria are the small bean-shaped power stations inside every cell. They take fatty acids and glucose and ketones and turn them into ATP. Like any machinery, they wear out. Damaged mitochondria leak electrons. They produce reactive oxygen species. They contribute to inflammation and to aging. Mitophagy clears the damaged ones and signals the cell to build new ones in their place. Studies in mice, including work from Beth Levine at the University of Texas Southwestern, who passed away in 2020 after spending her career on this question, showed that genetic disruption of autophagy accelerates aging. Genetic enhancement of autophagy extends health span. The pathway is real. It is conserved. It matters. How much autophagy do you actually trigger by skipping breakfast for 3 days? That is a harder question, and I want to be honest about it. But first, one more layer, because while all of this was happening, the glycogen draining, the ketones rising, the mTOR quieting, your endocrine system had been making its own adjustments. Growth hormone. Growth hormone is secreted by the pituitary gland at the base of your brain. In a fed state, the pulses are small. In a fasting state, the pulses get bigger. Michael Hartman and Johannes Veldhuis at the University of Virginia, working through the late 1980s and early 90s, demonstrated that a single 24-hour fast doubles or triples the amplitude and frequency of pulsatile growth hormone secretion. By hour 16 of a daily morning fast, plasma growth hormone is 2 to 5 times its baseline. Growth hormone has a peculiar role here. It is anabolic for tissues. It preserves muscle protein during the fasting period. And it is lipolytic. It accelerates the release of fat from adipose tissue. The body, in other words, is protecting your lean mass while it burns the warehouse. Norepinephrine. Norepinephrine, also called noradrenaline, is the catecholamine produced by your sympathetic nervous system. During a 16 to 18-hour fast, plasma norepinephrine rises modestly. The effect is to maintain metabolic rate, to preserve body temperature, and to sharpen focus. This is part of why some people report a clarity at the late stages of an extended morning fast that they do not feel after a heavy breakfast. The norepinephrine rise is real. It is mild. It contributes to wakefulness, insulin sensitivity, Each time you skip breakfast, the cells of your liver and muscles spend a longer period without insulin signaling. Insulin receptors recalibrate. Eric Ravussin at the Pennington Biomedical Research Center has measured insulin sensitivity changes in time-restricted eating studies in metabolic ward conditions. The improvement is real, particularly in people who started with insulin resistance. The effect after 3 days is small. The effect after 12 weeks of consistent practice is more substantial. And one more, because it matters. IGF-1. Insulin-like growth, factor 1. A hormone produced primarily by the liver in response to growth hormone signaling, but suppressed by sustained protein restriction. Walter Longo at the University of Southern California has spent decades arguing that elevated IGF-1 is one of the most reliable correlates of accelerated aging in mammals. Fasting lowers IGF-1. 3 mornings of skipping breakfast does not lower it dramatically, but it nudges the level down. It points the body in a different direction. So, across 3 mornings, your body has run 6 or 7 distinct programs. The pantry has been emptied and rebuilt. The warehouse has been cracked open. The liver has manufactured a new fuel. The brain has begun, for the first time in years, to taste it. The cellular janitors have come back to work. The hormones have shifted toward preserving lean tissue and burning stored fat. The picture is coherent. The pieces fit together. Now I want you to slow down with me, because I have just told you a long chain of mechanisms, and not all of them sit on equally firm ground. Let me grade them for you. 4 levels. The first level is what I would call settled physiology. Things measured, replicated, and observed in human metabolic ward studies under controlled conditions. Glycogen depletion in the first 16 to 24 hours of fasting belongs here. So does the rise of glucagon and the fall of insulin. Lipolysis from adipose tissue. The appearance of free fatty acids in the bloodstream. The production of ketone bodies by the liver. The kinetics of beta-hydroxybutyrate. The growth hormone surge. These are not in dispute. Cahill measured them in the 1960s. Veitch confirmed them. Hartman and Velduis nailed down the growth hormone numbers. They are physics with proteins on top. The second level is moderately supported. The brain's uptake of ketones during a 16 to 18-hour fast. Yes, the transporter exists. Yes, ketone uptake scales with blood concentration. But the magnitude of the cognitive effect from that mild ketonemia, that is less clear. Some studies show modest improvements in attention and processing speed. Others show no effect. The mechanism is real. The effect size is variable. Same for insulin sensitivity gains over a few days of practice. The direction is right. The magnitude depends heavily on the starting point. The third level, and I want you to hear me carefully, is preliminary. Most of what we know about autophagy from fasting comes from yeast cells, from mice, from rats. The evidence that a 16-hour fast in a human triggers measurable autophagy in skeletal muscle or in the brain is suggestive, not conclusive. There is a study from 2020 in Cell Metabolism that measured autophagy markers in human muscle biopsies after a 24-hour fast and found elevated levels. There are not many like it. Most of the popular claims about autophagy from intermittent fasting are extrapolated from animal data and from longer fasts. And the fourth level is speculative. The claims you read in popular health writing, that skipping breakfast for 3 days will significantly extend your lifespan, will protect you from cancer, will reverse cognitive decline, those claims outrun the data. The mechanisms point in promising directions. The human outcomes evidence is thin. I will give you one specific honest example. In 2020, a clinical trial called TREAT was published by Ethan Weiss and his colleagues at the University of California, San Francisco, in JAMA Internal Medicine. They put 116 overweight adults on a 16-hour daily fasting window for 12 weeks and compared them to a control group eating 3 meals a day. The fasting group lost a small amount of weight. So did the controls. The difference between groups was not statistically significant. And worryingly, a portion of the weight the fasting group lost was lean muscle mass. That trial does not invalidate the mechanisms I have described. The metabolic switching is real. The hormonal shifts are real. What the trial tells you is that simply skipping breakfast, without paying attention to total food intake, sleep, exercise, and especially protein intake when you do eat, is not the magic intervention some have made it out to be. The mechanisms exist. Whether they translate into the clinical outcomes you actually want depends on a great deal more than the timing of your first meal. I am telling you this because I do not want to oversell you. The story is interesting enough without exaggeration. But I am going to tell you one more thing now, and this is the part that when I worked it out made me sit back in my chair. Rapamycin. It was first isolated in the 1970s from a soil bacterium found on Easter Island, Rapa Nui in the local language, which is where the molecule got its name. The bacterium, Streptomyces hygroscopicus, produced this compound for reasons of its own. Researchers found that it had unusual properties. It bound with extraordinary specificity to a single protein complex. The complex that quiets when you skip breakfast. The complex that allows your lysosomes to begin their cleanup. mTOR. Rapamycin clamps mTOR shut. It is a direct, sustained pharmaceutical version of what happens, in mild form in your liver and your muscles, between hours 14 and 18 of an extended overnight fast. Rapamycin is FDA approved for preventing organ transplant rejection. It is being studied at multiple aging research centers. Matt Kaberlein at the University of Washington has been one of the most public investigators, alongside the Buck Institute for Research on Aging and the Interventions Testing Program, funded by the National Institute on Aging. In Harrison and colleagues' 2009 paper in Nature, low-dose rapamycin extended median lifespan in genetically heterogeneous mice by roughly 9 to 14%. That result has been replicated. It is one of the most reproducible longevity interventions ever measured in mammals. A monthly off-label supply costs somewhere between $300 and $500 in the United States. It requires a willing physician. It carries side effects: mouth sores, lipid changes, increased infection risk at higher continuous doses. Skipping breakfast for 3 days does not equal a course of rapamycin. I want to be very clear about that. Rapamycin shuts mTOR down hard for the duration of the dose. Skipping breakfast nudges mTOR down for a few hours during the late morning of each fasting day. The pharmaceutical version is a hammer. The breakfast version is a tap. Both hit the same nail. The shape of the impact is different. The total daily exposure is different. The off-target effects are different. But here is the thing I want you to hold on to. The molecular pathway that aging researchers are paying hundreds of dollars a month to influence, the pathway being studied at the Buck Institute, at the University of Washington, at the National Institute on Aging, that pathway you can touch, gently, by simply not eating until lunch on a Monday, a Tuesday, and a Wednesday. The body's version is milder. The pharmaceutical version is stronger. Neither is free. The pharmaceutical version costs money and requires a prescription. The body's version costs you the comfort of a morning meal and the willingness to feel hunger for a few hours that you will eventually stop noticing. The molecule is called rapamycin. The pathway is called mTOR. The intervention you can perform tomorrow morning is called nothing in particular. Just an empty plate where breakfast used to be. There is a piece of advice your great-grandmother might have given you in a generation that did not yet have continuous food access. She might have said, "An empty stomach is a clear head," or "A little hunger never hurt anyone," or, in some traditions, "An empty belly is the best teacher." She did not know about glycogen phosphorylase. She did not know about hormone-sensitive lipase. She did not know about beta-hydroxybutyrate, or MCT1, or mTOR, or autophagy. She did not need to. She had observed something, a clarity that arrives at the end of the fast, before the meal, and she wrapped that observation in a folk phrase that survived through the centuries. The wisdom was correct. The mechanism is now visible. So, press 2 fingers against the right side of your abdomen, just below your ribs, one more time. That is your liver. Tomorrow morning, if you choose, you can let it work. You can let it run the small ancient program that sits at the bottom of your metabolism. 16 hours. 18. If you can manage it, lunch will arrive. The food will taste better than it has in years. And the small bell of clarity you feel around 11 in the morning, that is not in your head. That is your liver, your fat, your mitochondria, and your brain, all on the same call for the first time in a long time. 3 mornings. That is all I am asking you to consider. Tell me what you noticed in your body the longest time you ever went between meals.